Resampling can help rare classes while breaking probability meaning. Calibration with scikit-learn fixes the scores before you choose thresholds. This is the workflow you'll know how to run when we're done, which adjusts resampled probabilities back to the base rate and applies the correction to live scores. I'm Professor Pi, teaching AI foundations with simple Python. Imbalanced classification shows up everywhere: fraud detection, rare disease screening, churn prediction. You often end up with far fewer positives than negatives. A model can still rank the examples well, but its predicted probabilities stop meaning what you think they mean. That matters as soon as you want to set a threshold or decide which cases go to human review. A common fix is resampling. Oversample the minority so the classifier has something to learn. That usually helps ranking, but it also shifts the probability scale toward a balanced world. In plain terms, the model starts to believe positives are more common than they actually are. Calibration after resampling gives you both benefits. You still oversample during training to teach the model the rare patterns. Then you learn a small correction that maps those inflated scores back to the real base rate. It's like letting the model focus on ranking, then training a compact adapter to speak the correct probability language for production. We will build a tight demo that shows the problem and the fix on toy data. You will see baseline probabilities, the inflation from oversampling, a diagnostic calibration curve, a calibrated wrapper, and finally, a threshold that picks the riskiest 10%. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a baseline measurement to see how raw probabilities behave on skewed data. This snippet builds an imbalanced dataset and fits a logistic regression in scikit-learn to measure baseline probability quality. The make classification call crafts 4,000 observations with only 5% positives, establishing a pronounced skew for later fixes. Train test split separates a test fold so we can measure calibration on untouched data drawn from the same population. Logistic regression from scikit-learn then fits the raw data without any sampling tricks, so its predict proba output reflects the skewed training experience. Breyer score loss squares the difference between each probability and the true label, returning a single risk-aware error we can benchmark. The reported baseline Breyer value shows how inaccurate the uncorrected probabilities are before we intervene. Next, we show the common resampling approach so you can see how it shifts probability outputs. This example oversamples the minority class with imbalanced-learn before refitting logistic regression to show how probabilities drift. RandomOverSampler synthesizes a balanced training set by resampling positives until the class counts match, leaving the held-out test data unchanged. Using the same logistic regression settings keeps the optimization comparable to the baseline, so any differences come purely from the altered class distribution. Predict proba produces the new probability scores, and taking their mean reveals the typical risk that the model now believes exists in production. Calculating ytest.mean provides the real prevalence, so we can compare model expectation against reality. The printed oversampled mean prob and true rate pairing exposes how resampling alone inflates the probability scale. To quantify the mismatch, we examine calibration curves for both models and prepare for a calibration wrapper. This code compares calibration curves for the raw and oversampled models using scikit-learn's calibration curve diagnostic. We reuse predict proba to gather probability outputs from both classifiers on the untouched test split. Calibration curve bins those scores into quantiles, computing the average predicted probability and actual outcome frequency per bin. Import CalibratedClassifierCV here. Ready's the calibrated wrapper we will apply next, without revisiting the import. The high bin gap oversampled versus baseline gap output quantifies how severely oversampling alone miscalibrates top-end probabilities. Now we apply a calibration wrapper that learns to correct the oversampled model while keeping its ranking power. This snippet wraps the resampling pipeline with CalibratedClassifierCV to learn probability corrections for the oversampled model. CalibratedClassifierCV clones the provided estimator, so we hand it an imbalanced-learn pipeline that oversamples inside each training fold and then fits LogisticRegression. Setting CV equals 3 splits the original training data into calibration folds, keeping held-out folds at the true class proportions for reliable calibration targets. The sigmoid method trains Platt scaling logits on each fold, while ensemble equals false aggregates them into a single calibrated predictor for clearer analysis. The calibrated Breyer figure demonstrates that the wrapper restored probability accuracy that oversampling alone had degraded. Finally, we turned those calibrated probabilities into a practical decision cutoff and validate the selection. This example turns the calibrated probabilities into an actionable decision rule by targeting the riskiest 10% of cases. Calibrator.predictProba supplies the post-calibration scores on the test set, reflecting the balance-aware corrections we just learned. np.quantile finds the threshold whose top decile matches our desired review budget, making the cutoff data-driven instead of guessed. Applying the threshold with a Boolean mask selects exactly the records we would escalate to human review. We measure both the actual positive rate within that slice and the mean predicted probability to see if calibration makes them align. The selected actual rate and mean prob values match closely, confirming the calibrated scores can support quota-based decisions. In a real system, this maps to a triage service, where the model flags candidates and human review handles the top slice. The same pattern scales to larger data and to other binary risks without changing the calibration idea. Quick recap. Do the resampling step to teach the model to rank the minority well, then fit a calibration layer so those scores mean the real-world probability again. Use this when your data are skewed, you need to oversample to learn the rare class, and you also need reliable probabilities for thresholds. One caveat: calibration only works if your held-out calibration targets reflect the true prevalence. So don't leak resampled proportions into the calibration data. Next step: tune the calibration strategy by changing the cross-validation folds and trying isotonic versus sigmoid so you can balance bias and variance in the correction. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.